So welcome everyone to this month's seminar in the Gemini Center on Quantum Technology. Our speaker today is Henrik Koch from the University, from NTNU in Trondheim, and he will talk about convex electronic structure methods for non-adiabatic dynamics. So without further ado, please take it from here, Henrik.
Hey, thank you, Franz, and thank you for having me. So today I'm going to tell you about some recent developments we have been working on for about a year now. I will start with an introduction and then tell you something about conical intersections and what the consequences are when you have to approximate wave functions. Then I will describe a formalism that actually fixes the current problems, so both in coupled cluster theory and in Hartree-Fock theory, and then I will give you some perspectives at the end. So the people that has actually been doing this is these four people. Sarah, she's now at King's College. She was a PhD student and she got her degree last year. Erik is at Caltech, and Federico and Leo are PhD students at NTNU. So what I'm going to talk about today is really based on four papers, and they're listed here. And so if you are interested, then you can just go there and have a closer look at the papers. I will be referring to these papers 1 to 4 during the presentation. So what we are interested in is photochemistry or photophysics, where you excite the molecule from I don't know if I have a pointer here. I don't have a pointer. Where you excite your molecule from the ground state S0 up to an excited state, for instance, a pi star state, an S2 state, and then you get a relaxation back down to the ground state, and there are two possibilities. You end up in the same ground state configuration that is actually called photophysics, or you take another path on the excited state potential energy surfaces and end up with some different products. And in that case, we call it photochemistry. The challenge here for the theoretical description of this dynamics is really that when we solve the electronic Schrödinger equation, we encounter degeneracies, so-called conical intersections, and this puts very strong requirements on the methods that can actually be used to describe these conical intersections. Typically, you get breakdowns, and this is what I'm going to talk about today, and also about how to fix that problem. Now, a conical intersection is an accidental degeneracy, so it's very difficult to predict where they appear unless there is some specific symmetry in the system. Maybe your molecule has a specific symmetry, then it's possible to where the conical intersection will be, but in general, it's not possible. And the dimension of this degeneracy space can actually be understood from a very simple example that was already done by Neumann and Wigner back in 1929. So if we look at a 2x2 Hamiltonian, then in order to have a degeneracy, the two off-diagonal elements must be 0, and the two diagonal elements must be equal. This gives us two conditions that must be fulfilled in order to get a degeneracy. And so the configuration space, so the internal coordinate space, -2 is actually the dimension of the space where we have a degeneracy. Normally, you don't encounter them when you just walk around the potential energy surface because it is n-2. And this is also the case why there is almost no chance to have a conical intersection in a diatomic molecule, because there you only have one dimension to vary. But for systems with more atoms, so more degrees of freedom, they are widely spread, these degeneracies. Um, Typically, they are depicted in the following way. You have two directions where if you move along those two directions, then you lift the degeneracies. It's a little bit strange. I don't have a pointer here, but on the right there, you have a conical intersection point. So you have the point of degeneracy. So you have the two potential energy surfaces. And then you move in what is called the G and the H direction. And then you lift the degeneracy linearly in those directions. H is the nonadiabatic coupling element, and G is the gradient. These were explored in the early 90s, and I have put some central references there on the page. Now, the complication is the following. So typically when we do wave function approximations, we write a wave function as psi a good approximation, and then with a constant C0, and then we have a correction term, what is called phi c. If this wave function has a conical intersection in the full space, so in the full CI space, for instance, then when I make a circle around the conical intersection, the green curve on the right, then the wave function must accumulate a phase as I go around and must change its sign. And the complication arises now when my approximation A does not have a phase. Because the only possibility here is if psi f has to change the sign and phi a does not change the sign, then the constant C0 must change its sign. And this means that as it is kept real, it will pass through zero. And this means that there are actually points in the configuration space where that approximation to the wave function completely disappears. Now, one could say, what if A also accumulates a phase? That is certainly possible. For instance, we could have an open shell determinant, and then one of the orbitals in that determinant could change its sign when I go around the punctured line. But this means that that orbital must necessarily be paired with another orbital such that there is a conical intersection in the orbital energies. And that is what I have called the X here, the blue in the blue. Now the complication then is if those two conical intersections are not in the same place, but they are in different place in the configuration space, then I can always find an alternative path that actually does not include the red. And in that case, there will be regions where the A does not change sign. And so the C coefficients will be zero. And this means that if the two conical intersections do not intersect or is in the same point, then I will have regions in space where the coefficients C0 becomes zero. So you have to think about this, for instance, in Müller-Plesset perturbation theory, for instance, we start out with a closed shell Hartree-Fock reference. And in that case, what will happen for perturbation theory is that it will converge to an excited state because the exact wave function does not contain the reference. So you have this conundrum that when you try to do perturbation theory, you converge to excited states in some parts of the potential energy surface, and in other parts you converge to the ground state. And then when you limit your perturbation expansion, then you actually get a region where you try to converge to something in between. And Another problem is when we do coupled cluster theory, because in coupled cluster theory, we also use a reference function, and we employ what is called intermediate normalization. And in intermediate normalization, we always choose the reference function, so the Hartree-Fock weight of the wave function to be equal to 1. And in that case, there is no way that we can change the sign of the wave function. And so we get into a problem. Let me just show you this here for coupled cluster theory, that we have the coupled cluster wave function there with the exponential. So it's 1 plus t and then so on. And those components that are higher there, they are in the orthogonal space to the Hartree-Fock. So the T operator excites out of the from the Hartree-Fock state. And the Hartree-Fock state will always have a weight of 1. And the only way that we could make the wave function change sign is what we see down here. We have the plus and the minus combination when we get from two different directions of the wave function, is to choose this C plus and C minus to be very large, such that the one that we have in front can be disregarded. And this is exactly what you see when you try to run a conical coupled cluster calculation very close to a conical intersection, is that the T amplitudes, so the T operator, will diverge as we approach the conical intersection. So this is exemplified here. There is, we have two cases. We actually have two kind of solutions here. We have those with positive excitation energies, that is A. And you see as we go around a circle of the conical intersections, we get very strange behavior. And what happens there is actually that the amplitudes, or one of the amplitudes, become very large. And this is shown to the right with that this is the amplitude's size that diverges away. But another complication is here that there is another solution that has negative excitation energies. So you have two solutions, and when you try to run very closely to these conical intersections, the solution can flip between these two situations, and the potential energy surface looks very weird. So the question is, of course, how do we find these conical intersections if it is such that we have such a strange behavior? So Sarah and Erik, they devised an algorithm where we sort of used the fact that away from the conical intersection, there can be well-behaved portions of the potential energy surface. And so if there was some way that we could actually stay away from the conical intersection and then optimize the structure, that would be very interesting. And particularly, we are interested in minimal energy conical intersections. This means that the minimum energy you have in this space of degeneracies. In some cases, these points can actually be related to the dynamics of the systems, and it's therefore of interest. Now, one way then to do this is that you have the seam, that is the blue line, and then you place a tube around this seam, and then you do the energy minimization. You do that on this tube. This actually means that you have a level function, and you only need gradient information in order to do the optimization on the tube. So this was a very nice way to avoid the complications close to the seam. Of course, if you shrink the tube too much, then you get into the same problems again. But the question is, can you stay away from the seam and then still get reasonable conical intersection or minimal minimum energy conical intersection structures in this way. And this is actually what it turns out to be. Now, I don't want to go into the details of the optimization, but we only use gradient information in order to do the optimization, and you can look in paper 2 in order to see how that is done. So just here to show you 2 examples. We have on the top part is the size of this seam. So you have 0.14 EV that you add to your function. So you stay 0.4 EV away from the seam. And then you decrease it to 0.27. And then this is for CCSD. And you see that it's not much that the geometry actually changes. You get small change of the angles. If you then do the same for SCCSD, that is a method where we have actually corrected the problems with the conical intersections, then you see that we get very similar results. So this is the method that we have used in order to locate those conical intersection points that we have studied. So what can we do in order to fix this problem? So the problem with coupled cluster theory is that when you try to solve the omega equations, then you get into problems. And the reason is really that you have this nonlinear set of equations that you need to solve. And then you can do a Taylor expansion in order to understand more about what is going on. And if you do that, then you have this expansion, you get this A matrix as the first derivative of the omega condition. This A matrix is actually related to the excitation energies in coupled cluster theory. And when you want to solve this equation and you have an almost zero excitation energy, which would mean that you have an intersection with the ground state, then the higher order terms dominate, especially what we have in the second equation here, that we have omega k along that eigen component of the A matrix. And then you see that I get omega k is the excitation energy. And if that is zero, then the higher order terms in this expansion will dominate, and then you can get bifurcations and multiple solutions and complex solutions as well. So using this fact that we have this problem when we have a zero eigenvalue of the A matrix, we came up with the idea that we can actually project out those components in the coupled cluster wave function. So this is just for your repetition here, equation of motion. We diagonalize a similarity transformed Hamiltonian, and this is how we get the excitation energies as the eigenvalues of the A matrix. Because A is non-symmetric, we have left and right eigenvectors, and this means that the projection operators we need in order to project out a certain eigencomponent of the T amplitudes is in a bi-orthonormal basis. So you have both the left and the right eigenvectors. And then you can project out the T amplitudes, as I have written there at the end, and then remove the critical components in the T. So you also then need to, because you now have one component less in your T amplitudes, you need to change the projection manifold that you use in order to solve the coupled cluster equations. So you simply remove those components in the left and the right projection manifolds. And then we actually get what we call generalized coupled cluster optimization conditions, omega tilde here, where we have changed the projection manifold and we have changed the T amplitudes in the coupled cluster wave function. And this, of course, means that we need to determine the eigenvectors and the eigenvalue at the same time as we solve the omega equation. But this guarantees that we actually have a convex optimization problem, so that the A matrix is positive definite in that space, in that reduced parameter space. But now we have, of course, removed one excitation that is still important in the system, and then we reintroduce that problem by diagonalizing the Hamiltonian, the similarity transformed Hamiltonian H bar here in the full space. So we add in that excitation again when we diagonalize the Hamiltonian, and in this way we also get the full CI, because now if the space is the same size as full CI, so we have for CCSD we have 2 electrons, then this matrix, when we diagonalize that, then it gives the full CI energies as it should do. This is described in paper 3. Now, if we look at some concrete examples here, this is for the ethylene molecule, where we have done some circles around the conical intersection. We see those problems that we had here in A, is for positive excitation energies. And we get these divergences when we reach the point where the reference should go to 0. In the below, in C, we have the reverse situation where we have negative excitation energies. Again, that one also fails when we try to traverse around the circle. It just has problems on the other side of the equation. And then, so this was CCSD we had on the left here. Then we have in D, we have GCC, and you see that the full lines, the blue and the red, that have the correct behavior. There's no problems with divergences. And also we have a positive excitation energy indicating that the A matrix is positive definite. If we look at the B, that gives us the projection of the left eigenvectors onto the T amplitudes. And there we see that it's clear that there is one component in the T amplitude that tries to diverge. This is the blue curve, and the others are well behaved. So also we have the correct description of the geometric phase. So when we diagonalize the full space matrix, we actually get the right change of sign of the when we do one circle from 0 to 2 pi. This you can see in the middle here that we get the right change of the sign. And then if we do a change to so you have the x1 and y1 and x2 and the y2, these are the components in the reduced space where we just diagonalize the 2 by 2 part of this matrix here. And we see that they change sign at 2 pi, and then when you continue until 4 pi, you end up in the original, with the original sign. So how does this method work then? Well, here you have some examples for lithium fluoride. So lithium fluoride, when you try to dissociate that, then there is a conical intersection at very long distances. You have a crossing between the first excited state and the ground state. And the thing is that this is because you get a larger and larger dipole moment. You dissociate into lithium plus F minus. And so the first excited state is forced down, and then it intersects with the ground state, and then you get an avoided crossing. And this is very difficult to describe, but the GCC does that in panel A here, does that perfectly, whereas in B and C you have the CCSD, and depending on where you start from, then you get different situations. So for instance, in C, you start from the right, and then you move into the left, and then you see that a very strange behavior of the different solutions. On the other side, you also get a strange behavior when you stretch the molecule. And you can see that they are very different, and this is exactly the two different solutions that I was mentioning before. Now we can look at the conical intersection in the ethylene molecule, and to the right we have the conical intersection. Now, because the full space matrix is still non-symmetric, then there will be complex eigenvalues when you zoom into this conical intersection, and this is what I have shown here to the right. But we know how to fix those things because we have done similarity constrained coupled cluster theory. We did that almost 10 years ago, and we do an additional similarity transformation of the Hamiltonian, and then we enforce orthogonality of the solution vectors over a positive definite metric, and then this is a sufficient condition in order for the matrix not to have defects, and therefore it has real eigenvalues. And this is what I'm showing here, is that when we combine GCC with similarity constrained coupled cluster theory, we can actually describe conical intersections that are real. Now, here is another example, another molecule. So it seems to work very nicely. We have studied many different systems, and we have no problems with conical intersections now with the TCC. Now, this was coupled cluster theory, and there is also some other theories that are maybe more basic, so, like Hartree-Fock theory, can also have problems with this. And the same key idea can be used here, is that once we optimize the Hartree-Fock state, then we can project out the components of the Hessian that we have here in E2 that have small eigenvalues or almost zero eigenvalues. And we can remove those from the Hartree-Fock parameterization that we have in terms of the exponential here and the kappa operators. So then again, we of course get a coupled set of equations where we have to determine the Hessian eigenvalues, project them out of the parameterization of the Hartree-Fock state, and then minimize the energy in that space. The advantage here is that it's size intensive, this process, because the Hessian matrix, when you diagonalize that gives you size intensive eigenvalues. And so the eigenvectors are size intensive as well. They only have components in the part of the molecule that where the problem is with the conical intersection or the small eigenvalue of the Hessian. And also you have complete orbital invariance because you project out the eigenvectors and not some particular orbital component. So in this way, you can actually regularize Hartree-Fock and avoid to get bifurcations and multiple solutions. Again, we project out this now single excitation component of the parameterization, and we can include that again in a completely similar way as we did with the coupled cluster. We just diagonalize a matrix with the Hartree-Fock and single excitations. So this is also what is called CIS, and it's this matrix here. And of course, one can also extend this and include other type of excitations. The computational scaling is overall the same as the standard Hartree-Fock, but of course there is a prefactor because we need to determine the eigenvalues of the Hessian at the same time as we minimize the energy. So if we compare here again for ethylene, this is S0, S1 conical intersection. you see the standard theory on the left is very strange behavior. We have two solutions. We have one solution with positive excitation energies, and then we have another one with negative excitation energies, and they don't coincide, right? They are not in the same place. However, if we look at the convex Hartree-Fock on the right, it's flawless. There is a nice conical intersection here. And this is the case where we have only projected out one eigenvector of the problem. So that is enough in order to fix the conical intersection with the ground state. We also look at, this was a relative plot where we plot them relative to each other. Here I have a full plot with the total energies. So you just see that this is a tilted conical intersection in this case. Now, let me conclude. So the thing is that because of these cases where the reference function, the Hartree-Fock reference function, completely disappears in the wave function that we try to approximate, we cannot consider corpus cluster theory well defined for all configuration spaces. And this means that, in my view, is that we should not really require it to be exact, but we should just require that it is a preconditioning of the eigenvalue problem. And then we should get the exact eigenvalues we should get from diagonalizing the similarity transformed Hamiltonian. If we do that, then we get a correct description of the ground state conical intersections. We still have size extensivity and size intensivity, and we have real excitation energies with this similarity constraint corpus cluster theory that I mentioned before. So we have two frameworks. We have generalized corpus cluster and we have convex Hartree-Fock theory. I think we will probably merge those two names and just call them convex because that is the case for both of them. There is also a path now because we can use the same strategy in order to do multi-configurational problems where we actually use state selection to choose instead of using the orbital spaces. So we can choose the eigenvectors of the Hessian in order to construct active spaces for calculating multi-reference cases. So the problematic case here with Müller-Placer perturbation theory is that it actually converges to an excited state. I didn't talk too much about this, but it does this in an n-1 dimensional configuration space. So this, of course, implies different constraints on how you can do perturbation theory and how you can determine excited states also using perturbation theory. We have already done convex DFT, and this is now ready to be submitted, and it works just as nicely as the convex Hartree-Fock. So we hope that will prove useful in the future. And then we have, I guess we can say that we have now solved the problem with conical intersection in corpus cluster theory. I'm not sure about the timing I have. I think I'm over time. Maybe I can just leave you because we have already done dynamics with these methods. And maybe I can just show you this plot for thymine where I have we are now able to meet the experiments where they actually, what they measure. So on the left, you have the experiments of a time-resolved experiment with thymine, with the relaxation from the ground state, from the S2 state to the ground state, or the S1 state here. And you see that the feature at 526 eV, that is a core oxygen core excitation, rises up. And then on the right, we have with corpus cluster theory a simulation of the similar situation. So I hope we will soon be able to do this for these generalized methods and then be able to describe the non-adiabatic relaxation all the way to the ground state. So I think I will stop here. And if you have some questions, please let
First
me
of
know.
all, thank you very much for this very interesting presentation, Henrik.